Hello! Welcome back. Hope you all are doing well. I'm pretty excited to be getting back to Essentials of Compilation today in Gleam, and we're getting into the meaty stuff. We did over the last 3 months or so. We did the very basics, and arithmetic is great. But we want to make more interesting and complicated programs than just things that add and subtract integers. So we are working in the chapter on conditional expressions and Booleans. It's chapter 4 of the book. And last time I did a little bit of extra long stream, partly because I was excited about the topic, but also because I knew I was going on PTO. So we did not have a stream last weekend, but I'm back and we can do a bunch today. So last time we created the elif language. So this is a language that has Boolean types and conditionals, and it's built on top of the elvar language, or it's kind of an extension of elvar, which had variables and integers. And so now we have two data types in our program, and we added a type checker for that, as well as an interpreter. So that was a pretty interesting session. And let's have a look at what we did last time, and then we're going to continue with this chapter and see what else we can build. So let me switch over to the coding screen. If this is your first time here, feel free to check out the GitHub repo Sean Cribb's Essentials of Compilation. This is where I am pushing every commit that I do on stream. So you can see this repository as it grows, as we do more with the compiler that we're building. We are also using the book. So let me see, we're at 4.3. Let me scroll back to the beginning. If you haven't seen it, it's called Essentials of Compilation, so no surprise. And if you are not familiar with compilers and this is your first time seeing my stream, I highly recommend you go watch the other sessions in the stream to get an idea of what we're building. It'll make a lot more sense. That said, okay, so last time we did this type checking, and we can see our, or did we do the type checking? Did we just do the interpreter? Let's have a look. I'm trying to remind myself. So we had the elif language, and here's its interpreter that we wrote. Okay, we did do a type checker, right? So it's a very simple type checker since there's only two types. So we can, we're checking the individual expressions, the operators within primitive operations, and and then we are getting a type for the whole program. So one of the things that is interesting about this is that with the calling convention and so forth that we've established in our previous languages, intermediate languages, the result of the program has to be an integer. So we can't return a Boolean. And if our program type checks to a Boolean, then we produce a type error. So that makes it kind of interesting in that we can interpret the programs, but we can also type check them and show that, like, if this produced, it does this comparison operation with the less than operator, and we know that that's going to produce a Boolean, even though we have this, this let expression around it that binds 42 to x. we know that the tail of that expression is a Boolean type, just intuitively. So there are some tests we didn't write. So we wrote a bunch of type checking whole programs. And let's see about, I'm trying to recall what we wanted for internal expression type errors. Oh, okay, so this is where maybe the type of the program is okay, but like down in a single expression you have a type error. So like let's see, maybe we can come up with some. Yeah, because I labeled this stream 4.2 plus, and oops, not thumbnails, table contents. 4.2 is type checking, so we want to make sure that we can cover a bunch more cases with our type checker, and of course happy path cases. So yeah, let's do a little bit more testing. Okay. So if type check expressions test, tests in Gleam have to be suffixed test, otherwise they will not be run, and they need to be pub. Okay. Yeah, it's just saying to you. Okay, so let's do let's come up with an example of something that would be an expression error. So this could be like we compared, and I don't know that we did this up here. These are just the programs themselves. Yeah, this is just type checking that the the return or the type of the whole program needs to be an integer. So what we want to do here is construct some programs where we're using operations with invalid arguments. For example, like doing a less than against a Boolean and an integer or something like that. So that's a good example. Maybe let's do if, and we're going to say less than 42 true, and then we're going to have it return 0 or 1. Okay, so this should produce a type error. And this is, we expected an integer, we got a Boolean, and the expression will be less than 42t, except it should, we need to express it in our intermediate languages data structures. So less than int 42 and bool true, right? So that should be the type error. Let's make this program. So program if, and this is prim comp less than int. So here's the expression where the type error should be produced. Bool true. Okay, and this if takes 3, int 0, int 1. Okay, so if we type check that, should equal error, and then this type error. Let's run that test and see if it passes. Okay, so So note that it's not at the next level of expression, it's at the deepest expression. So I did have that wrong. I wonder if there is value, because that's not really that useful from a type checker perspective. All of you who are familiar with Gleam's type errors or Rust type errors will be like, yeah, that, true, that could be anywhere in the program. That is interesting though. Let's go look at the checker and see why that is. So if we go down here, type check expression. So if, right, so we're doing this cascading result.try. But it's actually in the condition. So if we do type check op, let's go there. If compare, right, so this is, we're doing the use syntax, which does an early return for these particular these particular results. So if the first one does not, right, we're not using equal, so we can't compare that they're both Booleans, right? In this case, if we get the get the type of that, and then we check that it's equal to integer. So if this one fails, you're only going to get, so we go to this definition, right? It's taking the expression here, and there's not really a way to say okay, so we could change this such that it returns the whole expression, but then it won't tell you which sub-expression failed the type check. The flip side of it is, which is the current situation that we're in, is that we're returning the exact expression that failed to type check, but we don't have any of its context. So what might be interesting is for us to change the type error type slightly, such that you get the expression, but you also get the context. Or optionally the context. That's something to think about. I actually think this is fine as is, because this is such a small language and we're not writing big programs in it. But longer term, we're probably going to want something with a bit more detail here. So we might, via other phases of our compiler, have some context information passed in with each expression. We might have, this is the the line and column that it's at, which is what a lot of compilers do. Or we might have this is the surrounding expression, or what's the word? So in Haskell, there's and in a lot of functional languages, there's an idea of a zipper, which is when you're traversing a data structure, you get the item from within that data structure, and then the before and the after that kind of gives a context. And this works for both for things that are sequential, like a list or a set, but also things that are nested. So you could get what is the parent tree and what is the subtree, and that would be useful for returning errors that are actually helpful. That said, this is not wrong per se. So I think what we'll do is we will leave this and let's just make some other errors where the type of the program is not the problem, but the type of the an expression inside it is. So I want to come up with another one where you have a Boolean and an integer participating in an expression where they can't both participate. So let me split this right so we can look at the stuff in here as well. So looking at this, what might be useful is something where we have variables that have determined types, and then we type the expression in the tail of the let, in the body of the let. That might be a useful thing to do. So let's make some examples here. If we say like let A is going to be the let's add 5 and 10, and then we're going to do a greater than a 30. Okay, so we know that, except that's going to succeed. Let's do equal a and false. So equal is defined for Booleans. The other comparison operators are not. But we know that a here is, because of this sub-expression, which is an integer, type text an integer, that a should be an integer, and equality between integers and Booleans does not type check. So we should expect this to be a type error, and we expected an integer, and we got a Boolean, and the expression is bool false. Okay, let's see here. The other one that I was thinking of is that the then and the else branches of an if should have the same type, right? Otherwise, you can't unify the type of the if expression. So let's do if, and it doesn't really matter what goes here, 10 equals 2, then false or 42. Okay, so that's a pretty simple one. And what we would expect here is that we expected a Boolean because the then clause has a Boolean in it. We got an integer, and the expression was int 42. Okay. Let's see. What's another example that we can construct that would be useful? This is probably good enough in that it covers a lot of the paths. Let's look at, so we have if, we have let, we have primitive operations. Let's look at ops. Oops. We could do something where we, this is a pretty simple one, but we do not. Yeah, let's do some Boolean operators against integers. So let's do if, this would be and false. Well, yeah, that's fine. We're not evaluating. 1 or 2. Okay, so that should be a type error. We expected a Boolean, we got an integer, and it was 42 again. Aha, I knew it. Now, what was the question? Okay, so you could do the same with or. I'm not going for 100% coverage here, but we should do something like or read true and then 0, 1. So this, read is of type integer, the result of calling read, and so that should not work with or. So we should get type error, Boolean, integer, and then we'll have prim of read. I think that should be sufficient. So program let a, and we have prim plus int 5 int 10, and then we have prim compare equal var a and bool false. Okay, so I need to import those eq var. Okay. And then we're going to type check program and should equal. And this should be our type error. Except we need error, right? Okay. And let's go ahead and do the next one. So this program is if, and that is comp eq int 10 int 2 and we have bool false and int 42, and then we'll just copy pasta that. One thing we could do potentially is like make a table-like test, but I'm okay with these being separate instructions right now. Hi, Chris. Is your game jam over? Did you finish? How did it go? I was actually kind of jealous that I didn't have time to do that. I don't know what I would do, but I kind of miss programming in Bevy, or with Bevy. So I hope you had a good time. Okay, so we're doing and here, and this is taking a bool false and int 42. It ends next Sunday. Oh, 1 of 9. Okay, well, I thought it was like a 2-day, weekend type thing. Very good, very good. So that's a little bit less stressful, I suppose. Okay, so int 1 or int 2. Helps if I type correctly. Okay, so there's a valid expression, at least syntactically, and should equal type error or error, type error, and we expected a Boolean, we got an integer and int 42. One thing that's interesting about this that I'm noticing too is that yes, this is a type error. Oh no, wait, no, I was thinking about this one, not this one that we just did where it's in the conditional. But what's interesting about this is we don't have, it's not a true unification, because what we should be saying here is bool false is the problem, but the ordering of when we are evaluating the types is like left to right in the syntactic sense. So what we're getting here is that we were expecting a Boolean, but we got 42, except that the entire contents of this expression should be an integer based on what the type of our program is. So like there's no input to, I'm expecting this expression to type to an integer, and then the entire expression types to a Boolean but has this internal error. So like there's a lot of stuff here that we're not doing. It doesn't really trouble me that much, but it is sort of eye-opening to the potential issues that we'll find later when we do a more robust type checker. So fun times. Okay, we've got our last example here in the internal expressions that are not program level type errors. So let's get that done. Okay, so if we have or of primitive operation read and Boolean true. Okay, and then we either return 0 or we return 1. Okay, so what did I do here? Oh, I didn't import or read. I was like, yeah, that's an expression. Just import those variants so I don't have to qualify them. Okay, we're going to type check the program and should yeah, I was considering using should be error, except that it doesn't have, like we'd have to do should be error should equal. That's probably not worth. Let's just should equal. So we have an error and it'll be this. All right, let's run that test. Okay, so what did we get here? Interesting. That is not what I expected. So for this one where we were expecting bool false to be the problem, we got the expression and I think that we can show why. So comparison equal, it's like, does this expression type check? Sure. Does this expression type check? Sure. What we did was we took the original expression, and this is maybe something that we can do in other cases as well. But where's that let expression? Right. So here it's this part that is different. It's that we're getting the whole thing. I don't know how I feel about that. One possibility is that let's see if we're doing that anywhere else. I don't think we are. This really only comes down to the fact that for EQ, these two types could be different, but for the other operations, we're checking that they're equal to integer on each of them. Just here, we're checking are they equal types. So we could put B1 here. Yeah, so we could either put B1 here and be consistent with everything else, or we leave this and just have it be the ugly duckling. I'm not saying one way is right or wrong, right? I kind of want to make sure that we're consistent. And honestly, it's like we're doing it is kind of a depth first, right? Check. So I think I'm going to change this to be B1. And oh, and then now I get a different one. So are we doing it on if as well? Let's see. Yeah, we're using the whole expression. So here's a case where I would say E1 for the else branch, because the else one is the one that doesn't match. Technically, if we're assuming this kind of left to right evaluation there. This is interesting. I made some decisions last time that are showing themselves to be inconsistent. So, okay, so now it fits the pattern that we expect. Obviously, in this case, which one was failing before? Right, we got the whole bool false. So is this one. We were expecting just 42, but we were getting the entire if. I think the only problem with this, like, it's useful to have that context, but with this one, it's telling you I expected a Boolean and I got an integer, but it doesn't say which part of the expression that's in. So I think it's probably better to return the int 42, even though that's without context. And the only way that we could really make this sort of error better would be to make our type errors potentially specific to the kind of error that we got. But not just I got, or I expected this, I got this, and here's the expression. But in the case of if, you might have multiple variants where you might say the condition was not a Boolean. The other one might be the if or the else and the then and else branches have unequal types, which is a little bit better than just this, expected got expression thing. Okay. Well, we've got our errors. Without deliberating too much on it, let's make a happy path test. If type check happy path test. Okay. Let's come up with some programs that exercise this new functionality and do type check. So we want to make sure that the programs always return integers. We want to make sure that we don't mix and match integer and Boolean operations. And then we take advantage of things like let bindings, which induce a type on the expression of body, or rather inject a type into variables for that body. We also want to make use of if for branching, and the various new operators that we have. So comparisons and and or. Okay. So let's make a simple one that is like, I think I got that backwards up here. Let of the square braces. I don't write racket. I think it's like this. I don't know. Honestly, don't see. Like, I think it's closure that uses just square braces without the extra parens. I think that's makes a little bit more sense. You could also do it as, a list of pairs, or it could just be like, dot like that. Some Lisps do that. Anyway, some like I think Emacs Lisp has this let star where you just give it a bunch of pairs, and it it cascades. It actually creates a sequence of lets internally. But I'm getting off the beaten track here. Let's stay on task. Okay, so let's make x is 10 in or we can make it more interesting. Let's do x is read. So we read something from the standard input, which should be an integer, and then we do an if greater than or equal to, here I'm doing 42 again. That's fine. It is the answer to the universe and everything. Okay, so this should okay. So we know this should return an integer. This Boolean or this operator here, this comparison will return a Boolean, so that type checks. Both branches here are correct. We have a binding on a variable which is an integer, and then we are filling that into this expression. So we should get okay. So let's build this program. And honestly, this covers so many of the cases. Maybe we want to introduce some ors and nots and so forth. Yeah, maybe we'll do not in another example. Okay, so we're going to do let, and we're going to bind x to the primitive operation read in the expression if, and this is a primitive operation of greater than equal. Here, that's fine, we'll fix it in a second. Int 42 variable x. Okay. And then we're going to do a primitive operation of plus variable x with integer 5. One thing that we didn't do up here was we didn't check for unbound variable, but let's unbound variable. Let's make a new example up there in a minute. All right, I'm going to close this so we can see more. Okay, so we have our program. We let x be prim read, and we evaluate an if. Here's the conditional, greater than or equal to. Then we do this. else we do primitive operation minus var x int 10. Okay. All right, so now I'm going to do that, and let's, okay, it doesn't like that. Let's just add GTE and minus here. That should solve that. Oh, this is comp. Thank you, emojis. Yeah, we need another paren there. Okay, so we're comparing greater than or equal to int 42 and variable x. Okay. So let's remove the to-do up here. We're going to pipe that to type check program. And honestly, we just say should be okay. Because we don't, the type check program, I think, doesn't return anything useful if, does it just return the program? Yeah, it just returns the program. So we don't need to check that. We just want to make sure that it returns okay. Okay, so let's run this test, and then we'll go back and we'll make an unbound variable test. I'm just going to construct it, I think. We're going to do a primitive operation of plus, and that's going to be var a and int 2, and let's type check program should equal error unbound variable a, and let's import that. Okay. That's a pretty simple one to test. Let's run all our stuff. Okay. We are green. We probably need one more happy path. Okay, so let's do let A read, so we're going to read two integers. Let B read, well, let's just do one. And we're going to, let's do some compound Boolean expression. Let's say if and of a is greater than 5 and not, and this is going to be a dumb one, but a equals a 10. Okay, we could potentially have a not equal operation, but I don't think there is one in this language. Okay, so we have an if, and then if it's greater than 5 and not equal to 10, then we return a. Otherwise, we return, I don't know, 0. Okay, so let's construct that program. This does have we used or? No, let's use or. This does exercise, additional Boolean operations, making sure that like this returns a Boolean type, not is a Boolean type, this returns a Boolean type, that both of these are Booleans and so forth, and then the program also returns an integer. So I just saw your comment, Chris. Sorry, 8 minutes later. Yeah, detail into Emacs Lisp internals isn't on task, and probably is for this stream. Truth be told. Okay, so we're doing a let. We're gonna do a is the variable, and we're gonna do primitive operation read again. This looks like the last example. It does look like a last example. Okay, so we have if, and there's gonna be primitive operation or. And this takes two expressions, right? So this is going to be another primitive operation, comparison less than var a int 5. No, not less than, greater than. Greater than. Okay, let's go up and add that. Okay, so this takes two. Let's break this out into a new line so I can keep track of the nesting here a little bit easier. Okay, and then we have another primitive operation, which is not, and that takes another expression, which is a primitive operation, which is comparison, eq var a and int 10. Okay. And then, so we've got our entire conditional there. Otherwise, if that's true, it's var a. Otherwise, it's int 0. Okay. So one of the nice things about, at times it's frustrating, but one of the nice things about Gleam being so strict with its types is it's letting me know when I didn't complete one of these things that in Lisp it'd just be like, it's fine. Okay, and then I think that will cover enough examples for me to feel confident. And I do feel pretty confident about our type checker. I'm glad we found that inconsistency with the way that the expression that didn't type check correctly was returned. So that was useful. All right. Oops. Okay, I keep that up. So that's probably the most thorough test we've done in this entire series, honestly. We had multiple kinds of unhappy paths and happy paths, so that's good. So now let's look at the let's look at the C-if language. So this is section 4.3. It's going to be an extension of the C-var language. So similar to what we did last time, let's go ahead and more type checking tests. Okay. All right. And we can push that. Okay, C-if language builds on C-var by adding logical comparison operators to the expression non-terminal and the literals #t and #f to the arg non-terminal. Regarding control flow, C-if adds goto and if statements to the tail non-terminal. Okay, so let's look at C-var. And remember that C-var was you have, okay, so there's some info stuff, but in the body of the program you have a dictionary of blocks, essentially. This is like named spots in your program, roughly analogous to functions, but not exactly. And those all had tail expressions, and tails were either a return. So this is kind of expressing a list of instructions that are imperative as a like self-recursive data type, right? So you either have return, which is the end, or you have a statement and another tail. So a sequence which has a statement, and statements are always a sign, and this is probably where we're going to diverge, is that statements will get an additional thing probably. But this is what did they call that? It was like 3 address instructions or 3 address form. It's kind of an SSA type form. Anyway, okay, and then expressions were either an atomic thing or a primitive operation. Primitive operation, in this early version, the CVAR had only these 4. We're going to have more of those, I'm assuming. And then an atomic expression is either, an integer, so like a literal, basically, or a variable. So this was CVAR. So let's look at CIF, and what do they add? Okay, so atomic expressions also get Booleans. So let's just copy this, and we're going to make a new file, CIF. And let's just paste everything in. Okay. So we are getting, I'm going to split this so we can see side by side. So we're also getting Boolean. And what did I do in elif? Did I call it Boolean or bool? Bool, okay. Okay, so that's where we're getting our literals, true and false. So this is the concrete syntax up here. This is the abstract syntax. We really only care about the abstract because we're not doing lexer parser stuff yet. I suspect by the end of the book we'll be doing that. But honestly, even though it has its own interesting problems, it's probably the least interesting part of this compiler project. So, and also I feel like I've done lexing and parsing dozens of times before, and it's not, I won't say it's easy, but it's very familiar to me. So I like doing the bottom-up approach. Okay, so we get new atomic type of Boolean. I don't see an arg non-terminal. I think that's typo. I think they mean atomic. Okay, so we have more primitive operations. So I think this is going to kind of parallel what we did over here, except that the transformation that you do from what was the name of that phase that we did? The pass. I think it was remove complex operands. Yeah. It's either remove complex operands or explicate control. Yeah, so remove complex operands reduces such that you can have only atomic arguments. Yeah. Yeah, okay. So this is going to be a similar transformation that we needed to do. So there was plus, minus, negate, read. Right, so those are the expressions we had before. So let's add to the primitive operations. We have not, which is going to be an atomic. And then we have comparison, which we need to grab these, right? Comparison is going to be a comparison, and an A is going to be atomic, and B is going to be atomic. Note that there's It's interesting. There's not and or. There's not, but there's no or and operation. I wonder if this is turned into, because remember in our interpreter for last time we did short circuit evaluation, so they might turn or and into nested ifs or sequences of ifs with jumps, right? Okay, so I think that covers the primitive operations. We've got the comparison operators, the Boolean, atomic. So let's go to tail. So this is where it's going to change. We're going to have go to. The label is going to be a string. We're going to have if, excuse me. Interestingly, this has to be comparison. What? Let's read a little bit of the prose here. Okay, the condition of an if statement is a comparison operation, and the branches are go-to statements. Okay, so we have a problem here in that what we want this to be a primitive operator, because you can use this in assignments. So like you could assign the value of a comparison to a variable, for instance. But it's saying that if statements have to be a comparison between two atoms. So I think that the way, like, while this makes sense from the text of the book, I think we need our if statement to be stricter here. So it may syntactically look like this, but structurally it's you have a comparison operator, two arguments between those that are atomics, and two labels. I think that's probably the way to structure that, such that we don't get lost in the, like, oops, we dropped a read into the comparison position. That doesn't feel right. So let's make these. So comp is a comp. And then A is an atomic, B is an atomic. And then we do then is a string, and else is a string. And what did we do in elif? How do we label those? Okay, I called it if true and if false. So maybe we'll do if true and if false for consistency. That's interesting. The types are guiding us a different direction than the text. Okay. Right, so the C program contains a list of mapping labels to tail expressions. Right, so, you know, a go-to basically says, you know, if you are I guess you could have a go-to without any branch, but the point of the go-tos in this is the branch. Oh, the other thing, I guess, is jumping to a, so like if you have a branch and then they both do their own things but they don't return, you might want to jump to the continuation. Um, so your if true like creates a new tail that has the expressions that are inside, excuse me, the expressions that are inside the then branch, and the same for your else branch. And then those, if there's something that comes after that if, those jump to the continuation of that. So it is completely valid to have go to. The thing that I'm wondering is, similar to the problem of the condition, do we make go to its own type, and then we make sure that in the if true branch it's a go to, and if false it's a go to, and this is just go to, right? It feels maybe a little bit weird, because in this description here, it's kind of like a pattern match. Like your if statement, it has to contain this sub expression for the condition, and then the then has a go to, and the all right, let's not worry about it. I think that we might need to deal with that later, but let's not worry about it. Okay, going back to read it. Okay, so the condition of an if statement is comparison between, and the branches are go-to statements. It just means that I think we'll have to reconstruct that go-to and not use like the actual, literal value of go-to in that spot. And in order to make sure that we don't accidentally construct two independent tails here that we have to slurp out, we're not going to use the tail type on those branches. Okay. Go-to statement transfers control to the tail expression corresponding to its label. Right, okay. So there's also the x86 if language. All right. So we had x86 var, right? And this had some instructions. And we had x86 int, which is a reduced version without variables. So we're making another x86 language. Luckily, we had factored out the common stuff into base, which has like registers, locations, information about calling convention. It compares two locations for ordering. Converts the registers to like a rank for what we want to use, such that like it's saying don't use these. Just haven't ordering, honestly. Okay, so let's make an x86 if language. We delve further. Okay, so this extends x86 int. The interesting thing here is that we I don't think that we have variables in this one. We have literal integers, we have registers. Oh, and this is the offset. So int is like, this is the deref version, right? So let's look at this. Why don't we copy in our x86 if, and then we'll modify. Okay. Right, so these are the args. I don't know why they renamed that. I guess they didn't. Yeah. Okay, so args are immediate registers or derefs. That doesn't change. So what is this byte reg? Let's read. Okay. This is concrete. Okay, so we'll have to look at that byte reg, what that means. Okay, x86 does not provide direct support for Booleans. We take the usual approach of encoding Booleans as integers, true as 1, false as 0. Furthermore, x86 does not provide an instruction that directly implements logical negation. So elif, like not in elif and cif. However, the XOR Q, so Q quad word, instruction can be used to encode not. The XOR Q takes two arguments and performs pairwise exclusive OR operation on each, okay, and writes the result into its second argument. For example, applying XOR to each bit of the binary number 0, 0, 1, 1 and 0, 1, 0, 1 yields 0, 1, 1, 0. Note that in the row of the table for the bit 1, the result is opposite of the second bit. Thus, the not operation could be implemented with XOR Q, with 1 as the first argument, where arg is the translation of atom to x86. Okay, so right, okay. So they're saying, you know, whatever not of the atomic becomes a move and then an XOR with 1. That makes sense because if false is 0 and true is 1, if you pass false, XOR is going to give you 1. If you pass true, XOR is going to give you 0 because that, you know, that lowest bit is 1. Exclusive OR gives you 0. Okay. All right, so byte registers are just the 1 byte projections of the main registers. That's interesting because they need different instructions. Do they not? All right. Let us look. So this is the concrete up here. Yeah, I mean, so in 64-bit this would be RAX. But these would be the lowest 2 bytes of RAX. High and low. This is the weird thing when you have such a legacy ISA as x86. Because it was built on top of, like, you had 8-bit x86, and then you had 16-bit, and you had 32-bit, and now you have 64-bit. Like, you've got names for all of the portions of these registers. So, I don't know how we're going to allocate those. That'll be interesting. But so arg is a byte register. Let's just call it byte. Or are they capitalizing that? Yeah, they're capitalizing it. It's fine. Let's capitalize it. Okay, so this is a this is a byte register, and we're going to make, let's go over here to base, and this feels dumb because I feel like we have register, and these are all the 64-bit registers, but we might have 32-bit registers and 16-bit registers, and like whatever. Okay. We're going to make byte reg in here, and then we're going to type byte reg. Okay, and then this, they're only concerned with AH. Oops, I don't need commas there. AL. No. What was that? AL. BH. BL. CH. C. I'm tempted to like CL. Why do we have Erlang in here? Not used. Okay. DH and DL. The problem, the potential problem with this is that these, so like AH and AL, conflict with RAX because they are sub-portion of that register. That'll be really interesting when we get to register allocation. Yeah. Okay. So we have a byte register type. Okay, and we need this comparison type. We'll follow their lead and call it CC. I don't really like that, but we have E. Come on, man. Stop trying to be so smart. LE, G, and GE. And those are the equal, less than or equal, greater than or equal, or greater than and greater than or equal. Okay. And then we need to add instructions. I'm just going to put them at the bottom. We can sort them later, maybe. So A is an arg and B is an arg. And then we have comp Q, A is an arg and B is an arg. And this is one thing that I'm not sure about with x86-64 assembly, is that way back many years ago when I did 8-bit Intel assembly, we always used the comp instruction. And then we used, so what that would do on that particular processor, I don't know if this is the case with x86-64, but what that would do is that would set bits on a special register, which was like flags, right? See, the special E flags register, right? And then you would use jump, like JZ would be jump if 0 was the one that we used most often, or JNZ, jump if not 0, and like use that to do loops, right? So you would put something in a register, you compare that register to whatever your termination condition is with the comp instruction, then you would do jump JNZ. So like it would say, it would put 1 on the flag if they were not equivalent, or put 0 on there if they were, something like that. So I guess we'll learn further in this chapter why we have comp Q, but we also have these other these other instructions in here. Yeah, that was a great class actually, and working in 8-bit, where you only have 255 memory locations, uh, super interesting. I think we had a 12, it's like a 12-bit program counter. Yeah, so maybe you had more. No, no, you had like 256 bytes of RAM. Um, your yeah your program address could be bigger. So like I think we had 32K of program space. It wasn't very big, but since your instructions were at most like 3 bytes, it was not a big deal. Um, anyway, I am rambling. Let's get back to implementing. Okay, so comp q, we have set. That's interesting. Arg is atomic. Oh no, it's just arg. Okay. And then we have move zbq. And that takes 2 args. I guess that's conditional move. Like move if 0. Okay, and then we have jump if, which takes a comparison cc and a label, which is a string. Okay. All right, let's look at this. We talked about XOR for doing not. Next, we consider x86 instructions that are relevant for compiling the comparison operations. Comp q compares its 2 arguments to determine whether one is less than, equal to, or greater than. So this is what I'm expecting. Less than, equal to, or greater than the other argument. The comp q instruction is unusual regarding the order of its arguments and where the result is placed. The argument order is backward. Fun. So if you want to test whether x is less than y, write comp q yx. The result of comp q is placed in the special e-flags register. This is what I was expecting. Okay. This register cannot be accessed directly, but it can be queried with a number of instructions, including this set instruction. Okay, so really this set is like, is this flag set, right? That's kind of what I was expecting. Except that when we were doing the 8-bit assembly, we didn't directly test the flags. We usually used the jump if type of expression or instructions. So the instruction set ccd puts a 1 or 0 into the destination D, depending on whether the contents of the e-flags register matches the condition code. You know, E for equal, L for less, and so forth. The set instruction has a quirk in that its destination argument must be a single byte register. Okay, so this is why we have the single byte registers. And actually, I would argue that if that's the case, this should not be an arg. I think this should be a byte reg. And then you can only put, like, we just removed this, right? And you can only put byte regs here. Okay. Such as AL, L for lower bits, AH, H for higher bits. Thankfully, the move ZBQ instruction can be used to move from a single byte register. Okay. So this is move from a byte register to a quad register. That's really curious. I wonder if the internals of the processor are such that it looks like they're the same register, but internally they're not. So I seem to remember in 32-bit x86, you could just move stuff into, one of these byte registers or a 16-bit register, and then just use it from the 32-bit. Interesting. Okay. Okay. So that explains set. I'm glad that we checked that, because I think having this here will save us a lot of frustration. Because if byte reg is just an arg, then it means you could put byte reg in any of these instructions and it actually would not assemble. Like if this was a regular register and this was a byte register, I don't think that you would want that to work. So, okay. I'm going to put a little note here. The byte reg is only used in the set instruction, so it doesn't need to be a regular argument. And let's just take this whole thing and move it down a line. Okay, so we're not actually changing the argument here. We only allow set or byte registers in the set instruction. The other thing is, what to me that says, if this is same like left goes into right, move ZBQ, this should be a byte reg as well. So let's go ahead and say that's a byte reg. Okay. I wonder about the, and I think I had it here somewhere. Let's see if I've got the x86 cheat sheet. Where did it go? There it is. Okay. Oh, it's linked up here. So I wonder if there's information about move ZBQ in here. Let me bump up the size of that so we can all see it. Yeah, here's all the jump instructions, conditional moves. Move Z. Okay. Okay, so for example, moving a quad word, move Q. Some instructions like return do not use suffixes. Okay, others like move S and move Z will use two suffixes as they convert operands of the type of the first suffix to the type of the second. Okay, so convert the byte AL in the register AL rather to a double word in EBX with 0 extension. So that's what move Z is. So it's like you have this byte, pad the rest of it with zeros, that's the Z. It's a byte register and you're putting into a double word. Okay. x86, ain't you fun? All right, so that's what that is. So when we're over here, move ZBQ. This has to be byte register. And arg, we know all of our args are quad words. So it's either, we can't move into an immediate, but it's either a register, and our registers are all quad word registers, or it's a deref, and those are all quad word dereferences. So this instruction is only valid with a first argument, which is a byte reg in our case. Now, it could be potentially you might have an 8-bit deref or something. But I don't think that our compiler is going to produce anything like that. So, okay. That is an interesting thing to look up. Okay, so the x86 instruction for conditional jump is relevant to the compilation of if expressions. The instruction J and then some comparison operator, label, updates the program counter to point at the instruction after label, depending on whether the result in the eFlags register matches the condition code. So similar to the set, which was moving it into one of these byte registers, or setting that byte register to 0 or 1 based on whether this comparison was flagged correctly. This is jumping based on whether the condition flag matched. So, okay. It separates the instruction name from the condition code. For example, jump if le foo corresponds to JLE foo. Because the conditional jump instruction relies on the eFlags register, it's common for it to immediately be preceded by compq instruction. That's completely what I expected. Okay. So, there's not that much there. Okay, so we have the C-if language. We have the x86 if language. And we added byte register to base. Okay, so this is chapter 4.3, 4.4, add C-if language and x86 if language. All right, finally we're getting to a pass. So the shrink pass translates some of the language features into other features, thereby reducing the kinds of expressions in the language. For example, the short-circuiting nature of and. So this is actually similar to what I was thinking they were going to do with the remove complex operands was similar. So short-circuiting nature of and or logical operators can be expressed using if. So and E1, E2 is if E1, E2, otherwise false. Or this if E1, then true, otherwise E2. By performing these translations in the front of the compiler, subsequent passes of the compiler can be shorter. On the other hand, translations sometimes reduce efficiency of the generated code by increasing the number of instructions. For example, expressing subtraction in terms of addition and negation produces code with 2 x86 instructions, negq and addq, instead of just one subq. Thus, we do not recommend translating subtraction into addition and negation. Okay, so we're going to make a shrink pass. Let's see. Okay, so this is over the elif language. And it's translating, so this is elif to elif without and or. Okay. So what they're saying here about the tests, like there's a lot of stuff that comes with the course materials if you're doing it in Racket. Essentially what we should be able to do is take all of the stuff that we did in the elif test, so like all these examples, put the programs through the shrink, and they should still interpret the same way, and they should still type check the same way. So that's like a freebie in terms of our tests. So that'll be nice. It should not change the results of type checking or interpretation. In other words, does not change the semantics. Okay. So I'm gonna pull this back out. We're gonna make a pubfun shrink, and like we've done in so many, we're going to take, this is the input. We're going to take an elif program, right? And it's going to produce an elif program. Okay, and that's essentially, we're going to unqualify that. Okay. That's essentially what we're, what our shrink pass will do. So we'll make some private functions. I think that what we should do here is the elif program just has, where is that defined? It just has a body. So what we can do is go input.body, and we're going to say shrink expression. And then we're going to wrap it in a program again. And this is going to take, here. Okay. This is going to take an expression, and it's going to return an equivalent expression. And this will be recursive, so we'll do a case expression, and yeah, what we need to do is take care of all the missing patterns here. Obviously, if it's a literal Boolean, wait, do we have the right one? Oh yeah, here's int. Let's just put the, oops, let's put the literals up together. Let's combine those two. Okay, so if it's a literal, we don't do anything. If it's conditional, then else. What we're going to do is we're going to do let's import all of these. Unqualify. I'm sure there are an easy like import star, but I don't really think that there is. It's probably an anti-pattern, but since we're only dealing with one of them, one of our intermediate languages, we don't care. Oh yeah, and var is also one of these because it's basically a terminal. We don't need to recurse into it. Okay, so then we only have to care about if expressions, let expressions, and primitive operations. So we're kind of doing this top down. So let's do shrink expression, and condition is an expression, and shrink expression, then shrink expression, else expression. Okay, so that's pretty easy. For this one, v, and then this is the binding. Okay, let's call it var binding body, and this will do let var, and this can be an expression binding, and we'll shrink the body expression. And then the primitive operation, we need to go into it, and we're going to say prim shrink op of op. Okay, and here's where it gets fun. Okay, so this is what's wrong with that? Oh, is it just that I haven't implemented this? Okay. Let's get prim op. Type. Okay. Let's put a do in there and see if it, yeah, it stopped complaining about that. Okay. So let's match on the operation. And so here's the thing. We don't want to rewrap here because this should return an expression, because we want to be able to turn and into an if, but and is a primitive operation that contains other expressions. So the result of this should be an expression, and it just means that the ones that we're not expanding so really let's put and or up here, and then the rest of these we're going to combine into one big multi-pattern match. Except we can't do that. We've got to recurse into these. Never mind. Because these aren't reduced to atomic expressions. Right? We have to go into here. Okay. We're going to handle and or separately. But the rest of these we need to basically we need to do prim, and let's just pull in and or comp minus negate not plus read. I want all of those unqualified. Okay, and then we need, yeah, we imported prim. Okay, so this is prim of comp. C is just a comparison, so we can just pass it through, and then A is an expression, so we want to mutually recurse into that, right? And we're going to do the same for these. the main thing here is that we needed to promote the and and the or into their short-circuiting versions, which are expressions, not operators. That's why we're going through all this trouble. So negate. Okay, and not. M plus A and B. This one is just prim read. We don't need to modify that. Plus shrink expression A and shrink expression B. Okay, so now for and. Let's see what they say to do. And I think it's really, if is, yeah. So if A and requires both of them to be true, bool false. Right? So if A is not true, then you return false. Interestingly, if you know that A is not true, I guess you don't want the expression there. So I was going to say, if you know A is not true, then you just return A, but A is a whole expression because we're working with syntax tree. So here, if we do if A, then we put in a bool true, otherwise we do B. And the other aspect of it is that we need to do shrink expression on A and on B in both cases. Because we need to expand all of those out. So when we go to test this pass, I think what we'll do is we'll do both the semantics preserving test pattern, but we'll also have a few tests that are like, hey, if I have an and in here, then you're going to turn it into an if. So I think that those are, we'll start with those, and then we'll also copy pasta the stuff from the others and make sure that they produce the same output. So okay, and we're gonna slurp all this into shrink test, and we're gonna import Gleam unit should. Okay. Let's do shrink short circuit test. Okay. So let's make an example here that should be pretty straightforward. Let's do if and t false 0 1. Okay, really dumb one. So what we expect this to expand to is if t right? Not a very sophisticated one. Now we could wrap that with lets and so forth. Because if the first branch is true, then you evaluate the second branch. If it's not true, then you just return false. So that's how it should expand. Okay, so and let's import EOC passes shrink. Okay, so we're going to make a program of if, I guess I need to build. You were not expecting that. Yeah, okay. Well, let's wrap it in brackets. Okay. If we do if primitive and bool true, bool false, I'm gonna have to start breaking out the lines because I can't keep track of all this. Okay, and then there's the program. Okay, so the if needs int 0, int 1. And we're going to pass that to shrink. And we're say should dot equal. And then I'm going to copy this and modify it. This gets turned into another if. Bool true, bool false, bool false. Yep. Okay, let's run that. Okay, it was complaining we didn't use any of those. That's fine. But that one expands as you would expect. So let's do the same one, but with or. So if we say or, this should expand to if true, then true, and then whatever the b gets in there. So it shouldn't take too much to expand that. Okay, if bool true, true. Okay, and this is or. Or. Fine. Okay, so that one passes as well. So that's just showing the short-circuiting expansion of and or. And now what we can do is let's go over to this test and let us we're also going to import interpret and type check. Okay, so we're going to shrink preserves semantics, interpret test, and let's get basically all of these. I kind of want to make sure that there's I want to make sure that there's everything that we would yeah, this one, okay, so this one has an and in it. So that will be useful. We're going to need to import bool value. So that should expand, but also evaluate to the same result. So let's put shrink in there. Okay. And then the conditional, we're just going to make sure, let's import LT. Let's put shrink. All right, let's run those tests. Okay. Good stuff. Let us do type checking programs. So this is going to be a little bit tedious, but shrink preserves semantics. The interesting thing here is we might get different yeah, I'm gonna have to import all that type. Type. Actually, we just want integer Boolean type error, right? Okay, so that resolved those. This is not doing anything yet, though, so we need to run it through shrink. I'm just going to copy that and paste it in all these spots. Okay. Okay, so here's where we are actually changing the results of the type check. And that makes sense because this and is expanded to a Boolean. Right. So we need to fix that particular problem. That I think is an expected. Where's the prim and? Yeah, this is an expected error in the transformation. Because we've got a different way of expressing the same thing. Let's see if we have any other errors. Okay, so that one I think is worth calling out. This one is transformed by the pass. Okay. So that's fine. I think that, we can spot check just looking at this. Bool false went here, bool true went here, and then, if this one is false, it goes to this branch. So I think that that's the expected transformation. And also this is about type checking the program. This expression returned a Boolean type, and we're expecting an integer type for the program. Okay, so let's do the rest of these, and then we can call it a day, I think. This is pretty good progress. Okay. Fun. Shrink preserves semantics type check expression test. I'm getting really elaborate test names here. Okay, so we're going to need to import unbound variable. What else is wrong down here? We need EQ constructor. Yeah, okay. So now I'm going to go and put the shrink in all of those. And there. Right, and this one I think will potentially produce a different type error. Let's watch for that one. This also might produce a different type error. Okay. Yeah, okay, so we've got what happened here is this one flipped. And I don't know which line that is on, sadly. So we expected Boolean integer int 42. Is it this line? Let's look at this. And what we got was integer Boolean bool false. Right, okay, so, and, yeah, because this becomes the then clause. Actually, this is the one I didn't expect. So, I think that's acceptable because we are still doing the left to right on the type check, and this expression needs to be bool false. The problem is we're probably not type checking after this transformation. I just want to make clear here that we're getting a different type error because this becomes if false 42 false 1 2, and so what we're getting is this does not match, but there's no downward information about what type of expression is expected here, which is a thing that we could enhance in our type checker maybe later, is that you know, I got an expression that evaluated this, but I expected, based on the context, an expression that should be this type. That's also useful, but we don't have it in this spot, and so what we're getting is you know, type error that doesn't make that much sense. It's just saying I expected an integer and you gave me a Boolean which was false. So I think that it's fine to have, you know, to change the test to match the result, as long as we understand what the result means and that we're okay with that, because this is literally what the shrink pass does. All right, I feel pretty good about that. So that's source test. This is chapter 4.5. Shrink pass. Okay, I think it's a really good place to stop. Let me see if I can. I think it's complaining about things I didn't use here. Yeah, because I just copy pasted that stuff. Okay. All right, that's a really good place to stop. Next time, we will look into the uniquify variables. So this is going to have to, you know, there's not much here in this section, but it's add cases to uniquify expression to handle Boolean constants and if expressions. So I think that probably what this means is that, you know, this is an additive, this is an incremental compiler construction. Uniquify is going to have to take elif instead of elvar, and then we will add the things necessary to these case clauses, and then we'll have a new one that takes into account Boolean expressions, and then we'll go through the other passes that we already have. Remove complex operands, and then we're gonna have a new output language there. So elmon var, we're gonna have elmon if, just like we have elif and elvar, and so forth. So we'll go through all the rest of the passes, and then we'll deal with all of that stuff. So that'll be really interesting. I hope you can join me next time. I am going back to, since I had that PTO last weekend, I am going back to weekly, and so I will probably see you through the rest of the summer on this. Thank you so much for joining me, and we'll see you next time.